Everybody knows that ants dig nests in the soil and bring the excavated dirt to the surface, but how much dirt they move deserves a much closer look, and that is what this video is about. Why is this of interest? Water gradually leaches nutrients from soil and carries them out to sea, so left alone, soils gradually lose their fertility. The stirring of soils by animals such as ants delays this nutrient loss to the sea. In much of the world, ants are the most important stirrers of soil. If you live in the south, you're likely to have seen lots of fire ant mounds. You can find them in disturbed flatwoods where the water table is high. And you can find them in many places where people live and the ants are not welcome. But there are over 100 species of ants in the North Florida area where I live, and a lot of those make underground nests, often with distinctive soil dumps or craters. Many are not very conspicuous or not very common. Others are easily recognized and very abundant. They may be small, and the soil they bring up is soon washed or blown away. Some are so tiny that they are easily missed and take some careful searching to find. While others are huge and hard to overlook. The density of nests of multiple species is often quite impressive. A recent burn here has exposed hundreds of nest mounds previously hidden under a litter of pine needles. Even the density of a large conspicuous species such as Florida harvester ant can be very high. Piles of dirt on top signifies that there is a hollow space beneath the pile, the nest that the ants have built and in which they live. Just as the soil dumps vary in size and shape, so do the nests below. I've made these hollow nests visible by filling them with a casting material. The cast is to the nest as a photographic positive is to its negative. Here are a few examples of nest casts of a number of ant species that range from huge to tiny, from bulky to slender, from simple to complex. Large or small, massive or delicate, what all these nests have in common is that their construction moves soil to the surface or below it. Estimating soil movement for all ant species at a site is just not feasible, but we have done so for 2 species. The Florida harvester ant, Pogonomyrmex badius, is found at low densities and makes very large nests. Whereas the fungus-gardening ant, Trachymyrmex septentrionalis, makes small nests but occurs in dense populations. Because we know the size, depth, lifespan, and density of these ant nests, we're able to estimate the amount of soil these ants turn over. These data were accumulated over years in collaborations with several colleagues, Christina Quapich, John Seal, Jack Rink, and Jim Dunbar. We also had assistance from Nicholas Hanley and Julio Dominguez. The excavation and mapping of hundreds of harvester ant nests over many years provides the most important underlying data. No matter what their actual depth, the relative volume of these nests in relation to depth is very consistent. We can refer to these proportions as their shape. Relative depth can be converted to actual depth, revealing how much sand from each depth is deposited on the surface. Larger nests bring soil from deeper, shown as yellow to red, to the surface. However, the largest volume always comes from the upper parts of the nest, the blue and aqua. When harvester ants dug nests in 11 layers of colored sand, the surface appearance of colors showed the progress of the excavation, biomantling. The lower the band, the deeper the soil sauce. Red is about 2 meters deep. The ants also deposit 2 to 4% below ground. This is bioturbation. A link to my video on this experiment can be found on the end screen. To apply this to landscape scale bioturbation and biomantling, we also need to know the size distribution of colonies and the frequency with which they move. We collected these data by following 400 marked colonies for 7 years. The average size is 3 to 4 liters. The average depth is 160 to 180 centimeters. Colonies move about once a year on average, digging a new nest with each move. From these data, we modeled how much harvester ants biomantle over the years and how much of the biomantle comes from each soil depth, homogenizing the surface soil. Here we have the moves of harvester ant colonies over a century. Source of the soil is shown as blue surface to red deep. Simulated colonies die after 20 years and are replaced by new small colonies shown initially as blue. Colonies grow and deepen, bringing deeper soil to the surface. Wind and water quickly spread the soil disks to form a homogeneous even layer over the landscape, as shown by the spread of a disk of pink sand over a year. By 7 months, only pink smudges are visible. Within a year, pink sand is present in an area more than a meter in diameter. By 2 years, pink sand is detectable only as its fluorescence under UV light. Over a millennium, a colony and its descendants will bring about 2,500 liters of soil to the surface, with about 300 liters coming from deeper than 50 centimeters. Spread evenly over its territory, this is a layer almost half a centimeter thick, amounting to 64 metric tons of soil. Another 1.3 metric tons are deposited below ground. But the northern fungus gardening ant, Trachymyrmex septentrionalis, moves much more soil, even though its colonies are much smaller. In its optimal habitat in the Florida sandhills, there can be over 1,000 colonies per hectare. Even roadsides, such as here, have abundant populations. The ants fill 1 to 5 of their chambers with fungus gardens built of caterpillar droppings and plant debris. To quantify this soil movement, we set up a layer cake of 5 different colors, similar in design to the one we ran with harvester ants, link on the end screen. So this experiment is one in which we are trying to figure out how much of that subsurface deposition is carried out by this little fungus gardening ant, Trachymyrmex septentrionalis. They make little egg-shaped chambers, and we had observed earlier that the chambers are moved upward and downward, mainly downward during the summer. As the soil warms, they make deeper chambers, and they seem to fill the abandoned chambers with sand from below. So that led us to this experiment. So we've created a layer cake with 5 different colors of sand, which I'll show in a minute. And we've planted a fungus gardening ant up here in the top and forced them to dig within this column of colored sand by putting the colored sand in a curtain of polyester fabric so they can't get out. And they were caged here, so they had no choice, none at all, except to dig right here in this column of soil. So that was in the spring, March or April, and so they've been digging and doing their thing all summer, and now we're digging them up. We're looking for chambers, and we're going to see whether there are, well, we have 5 different colors of host layer. So if we find a chamber in, let's say, the orange layer that has purple sand in it, we know that the purple, which comes from below, has been deposited in the orange chamber. So we're able to not only see whether they move sand and deposit it without bringing it to the surface, but also how much, because we know what proportion of the grains are in each color, so we can estimate how much sand, you know, the grains that we count represent. Here John Seal has located a chamber in the yellow sand layer and collected the non-host sand from within it. The soil in the nest crater of a single Trachymyrmex colony is a pittance compared to that of the harvester ant colony. These are shown to the same scale. And its nest volume is a mere blip in comparison to that of the harvester ant nest, also shown to the same scale. Yet our experiments showed that each spring these ants bring 0.5 to 1.5 metric tons of sand per hectare to the surface, about 800 metric tons per. They mantle the soil surface with over 6 centimeters of soil per millennium, about 12 times the mantling rate by harvester ants. In addition, these little ants mix another 200 metric tons below the surface, bioturbation, about 150 times as much as harvester ants. Abundance thus more than makes up for small size. In the words of Yoda, "Judge me by my size, do you? And well, you should not." The 2 species in this video are only a small representative sample of the abundant and diverse ant fauna of the North Florida region. The soil moved by these 2 species is only a small part of the soil moved by the ant community as a whole. Over the millennia, soil is like a slowly boiling liquid with some plumes rising to the surface and spreading out, others sinking down, and others still roiling and turning beneath the surface. The main agents that cause this churning are the animals that inhabit the soil. By far the most important are the ants.